Hi everyone, welcome back. Today we're going to be working on Rolle's theorem and the mean value theorem. Now, Rolle's theorem takes into consideration a function that is differentiable and that is continuous on some interval. Let's call that interval from A to B. So what we want to do is we want to work with these functions that, number one, are going to be continuous on a closed interval from A to B, and number two, that they're going to be differentiable on the open interval from A to B. And then Rolle's theorem is going to say that we also want to identify that the function output, when the function is evaluated at the endpoints, are equal to one another. If so, then Rolle's theorem will guarantee that there is at least one number c in that open interval AB such that the function, the derivative of the function evaluated at c, gets a 0. Now, what does that look like then? Well, for us, or what we're doing, this is going to correspond to some function which we'll call just f of x. And this function is going to be bounded on some interval. Let's call that interval from A to B. So we'll go here from A to B. And what we want to do is we want to make sure that this function is continuous differentiable and that the output, meaning the y value for both of these functions, is exactly the same. Now, if this is the case, then Rolle's theorem says that it's going to guarantee that there is a number c inside of the given open interval from A to B such that the derivative of the function, or the slope, the derivative of the function evaluated at c is equal to 0. In other words, the slope of the tangent line will be equal to 0. Now, again, this is Rolle's theorem. It says that we will be able to find some value for c. Now, what's really interesting as well is the fact that we can take the same f of x function, and instead of having that f of x function being equal to f of a is equal to f of b at some random number, or at some random y value, we want to fix it a little bit more. And we want to make sure that our f of a and f of b is this axis here, which must be equal to 0. In other words, y is equal to 0. At this point in time, this function is still continuous, it's still differentiable on the interval from A to B. The only difference here is that the y values, the outputs, are both 0. Now, this is going to tell me that these values are going to be the intercepts. In other words, they're going to be the roots for the function f of x. So if we can identify the roots for the function f of x, then naturally what's going to happen is that we're going to be able to find some value for c inside of that open interval where the derivative evaluated at c is equal to 0. And again, this gives us a method to now find these critical numbers within this given interval. So that looks pretty good for what we're doing. All right. Now, it's only guaranteeing at least one number c in this given interval. Well, what if we had a function like this? And this was our function f of x. Well, if that's our function f of x, then if we can set some boundaries here, call this f of a is equal to f of b for that y value, then we'll be able to see here that we can bound by some number a and bound by some number b, but you're going to see that as we go through and we find the derivative here for the function, that there's going to be two places. There's two places where the derivative of the function, call this C1, is equal to 0, and that's at C1. And there's also a different value, call this f prime at C2, is equal to 0. And this is C2. So again, Rolle's theorem just guarantees, hey, you're going to find at least one. There could be more of these turning points, but you're going to find at least one of them. All right, so that's what Rolle's theorem says. And what we want to do is we're interested in verifying Rolle's theorem and working with it. So here we're going to have this example that we're going to be working with Rolle's theorem. So here goes the example. Let f of x be equal to x to the fourth minus 2x squared. And we want to find all values of c in the interval from -2 to 2, such that f prime of c is equal to 0. Oops, my apologies. I wrote this as a closed interval, and since I'm saying find all values of c in this interval, c, the value for c cannot be one of the endpoints. That's what this open interval means. So the bounded interval for the function is a closed interval, but the differentiable interval does not need to be a closed interval. That one can be an open interval. All right, so the first thing that I'm going to do is I'm going to verify Rolle's theorem to make sure that I can find some of these values. Because if I can't find any of the c values within this given interval, then my job would already be done, and I would just say, hey, there's no such value that exists because this will not work. So let's go into that process then. Okay, so the first thing that we're going to need to check is that the function is continuous. So we're going to say f of x is a polynomial therefore it is continuous, and I'm going to go ahead and slap this on as well, and differentiable everywhere. Well, since it's continuous and differentiable everywhere, then on some given interval, it's also going to be continuous and differentiable. Now we also want to check the endpoints. We want to make sure that the endpoints are equal to one another. Okay, if they are, then that's going to be great, and therefore we're going to be able to extract these values. Okay, so we can then start looking at f of 2 and -2. So I'm just going to write a quick note here. Note, f of x is an even function, so f of -x is equal to f of x. Why does this benefit us? Well, this benefits us because I don't need to evaluate my endpoints. This function, being an even function, tells me that f of -2 is going to be equal to f of 2. Therefore, all three conditions for Rolle's theorem are now satisfied. Rolle's theorem said that the function needed to be continuous on the interval, it needed to be differentiable on the open interval from -2 to 2, and it needs to have the endpoints equal to one another. Therefore, any value that I find inside where the derivative is equal to 0 must be those c values. So now we're going to go through and we're going to apply Rolle's theorem. So by Rolle's theorem, there exists at least one c that exists in the interval from -2 to 2 such that f prime of c is equal to 0. And this example wants me to find it. So we're going to go through and we're going to find it. We're going to need to take the derivative. So let's take that derivative, f prime of x. This is going to be 4x cubed minus 4x. Insert the c value. We now get 4c cubed minus 4c. We can factor out a 4c, and we're going to be left with c squared minus 1. And this factors. Therefore, we're left with 4c times c minus 1 times c plus 1. And we need to make sure now, because Rolle's theorem guaranteed that we were going to have some points that produce the derivative being equal to 0, we're now going to set this derivative being equal to 0. So 4c times c minus 1 times c plus 1 must be equal to 0, which will imply that c is equal to 0, or c is equal to 1, or c is equal to -1. Now, which values fall within the given interval? Well, the given interval is from -2 to 2. Therefore, all of these values will satisfy that derivative, or Rolle's theorem. Therefore, c is equal to -1, 0, and 1 all satisfy f prime of c being equal to 0. And we're done. That's it. We just wanted to find where are those turning points. Now, on to the mean value theorem. And for the mean value theorem, what I'm going to do is I'm going to write the theorem on here, and then we're going to start explaining it and talking about it. So stay tuned for that in just a little bit. Alright, so here's your mean value theorem. The mean value theorem says that if f is continuous on the closed interval from a to b, and differentiable on the open interval from a to b, then there exists a number c in the interval from a to b such that the derivative of the function evaluated at c is equal to the difference in between f of b and f of a, all divided by the difference of b and a. Well, that's intense, to say the least. So let's go ahead and let's dissect this just a little bit more. That way we can get more of a geometric representation of what it is that we're observing. And then we'll go through and we'll do an algebraic representation of what this work implies for us. So here we have y and here we have x. And I'm going to have some function here. Call this function f of x. We're going to make sure that this function f of x is differentiable and continuous. And then we're going to extract, or we're going to constrain this on a given interval. So put some constraints there from a to b, meaning that we're going to have an output here of f of a, and we're also going to have an output here of f of b. And this difference that we're looking at the change in the output divided by the change in the input. In other words, we're really looking at the slope of the secant line that is made by intersecting these points. So there we have our secant line. And again, the slope of that secant line is f of b minus f of a, all divided by b minus a. Great. Now, what the mean value theorem says, that somewhere along this interval, since this function is already continuous and differentiable on this given interval from a to b, so somewhere on this interval we should be able to extract that there is a derivative that when evaluated at some value c, and this value c will exist inside of the interval from a to b, that the slope of the tangent line will be equal to the slope of the secant line. So what we're looking for is the slope of the tangent line. This is going to be f prime evaluated at some c. Well, okay, notice my angle measurements didn't move, so this line is headed in a parallel direction to the secant line. And if I draw my line here as is, then this line is parallel, meaning that their slopes are exactly the same. The slopes, or the slope for this line, is the value of c that we're looking for. Mean value theorem guarantees that there will be a number c such that this happens. Could there be more numbers? Yes, there can. Or yes, there can be. There is another value, in this case, right over here. And in this case, we can produce two different c values for this theorem. It's not always going to be the case that you're going to find two of those values. However, it is the case in this particular picture. So this is the mean value theorem, and this is how we want to work with the process of identifying whether a function is going to satisfy the mean value theorem, and when it does, we want to find those values. So let's go on to an example. On this example, we're going to first determine whether the mean value theorem can be applied to this function f of x being equal to 2 sine of x plus sine of 2x on the closed interval from 0 to pi. If the mean value theorem can be applied, then we're just going to say find all values of c in the open interval from 0 to pi such that f prime of c is equal to f of b minus f of a, all divided by b minus a. So again, we're going to determine whether we can use the mean value theorem. If we can use it, then we're going to go ahead and apply it. So let's go through and let's see if we can apply it. There's really only two conditions that must be met for this mean value theorem. The first condition is that it must be continuous on the closed interval. Secondly, we must be differentiable on the open interval that is given. So I'm going to start off with the function. F of x is an addition of two trigonometric functions. Which are continuous everywhere. Therefore, or you know what, I'm going to say continuous and differentiable. Continuous and differentiable everywhere. Therefore, f of x is continuous on the interval from 0 to pi and differentiable on the open interval from 0 to pi. Okay, so we can apply the mean value theorem. So the mean value theorem is applicable. Got it. Perfect. So now we're going to go through and we're going to identify everything that we need. First off, we're going to need a derivative. Okay, so let's go ahead and find that really quickly. F prime of x is now going to be 2 cosine of x. Sine of 2x will then be, by the chain rule, 2 cosine of 2x. Awesome. I need f of b and I also need f of a. So I'm going to find those as well. So here I'm going to go with f of pi. This is 2 sine at pi plus sine at 2 pi. Both of the values, sine at pi and sine at 2 pi, are both 0. Therefore, we get 0. And I'm also looking at f of 0. 2 sine pi, 2 sine at 0 plus sine at, again, 0 will give us 0. Well, look at that. That's awesome. So in this particular example, this mean value theorem is kind of turning into Rolle's theorem, because Rolle's theorem, this actually satisfies Rolle's theorem as well, that says that both of the evaluation of these endpoints must be the same, and it is. But again, we're using just the mean value theorem. And Rolle's theorem is just a mean value theorem in disguise. Okay, so now that we have all this, I want to substitute in my f of c value here. So let's go with f of c. That way we can find this c value that we're looking for. All right, perfect. So now let's go through. Let's go through and let's start evaluating this. All right, so I'm going to take f of c. I'm going to take my f of c here. That's 2 cosine at c plus, f prime of c. 2 cosine at 2c. And I'm going to set this equal to f of b minus f of a. So just as a quick reminder, f of b is here, and this is f of a here. Oops. All right, there we are. So f of b was 0 minus 0, like that, divided by pi minus 0, which means we're going to get 0. So in this particular instance, we now have 2 cosine at c plus 2 cosine at 2c is then equal to 0. And we have to go through and we have to find the values that this satisfies. So naturally, we have this cosine double angle for cosine, and I'm going to use a double angle for cosine, and I'm going to extract this. So I'm going to say double angle for cosine squared. Now, not cosine squared, for cosine 2 theta. Remember, the double angle for cosine 2 theta has 3 different representations. It has cosine squared theta minus sine squared theta. All right, that's one different representation. And I don't think I want to use this representation here. All right, the next one, if you substitute in cosine squared is equal to 1 minus sine squared, then what you're going to get is 1 minus 2 sine squared theta. And because I have another cosine, I don't want to use this one either, which means I probably want to use the last one. And the last one's going to be inserting sine squared. Well, minus sine squared is really going to be cosine squared minus 1. So this will now be cosine, this will now be cosine squared theta minus 1. 2 cosine squared theta minus 1. My apologies. And this is a value that I want to insert into my double angle here. So 2 cosine of c plus 2 times the double angle that I am inserting here, which is 2 cosine squared of c minus 1 is equal to 0. Distribute everything, and we're going to have 4 cosine squared c plus 2 cosine of c minus 2 is equal to 0. And we can divide everything by 2 to get us 2 cosine squared c plus cosine of c minus 1. And we're going to check to see if this factors, because this now is in quadratic form. If it's in quadratic form, it should hopefully factor. Not should, but hopefully it'll factor. Alright, I have a 1 here and a 1 here, and if that's a minus, then one of them has to be a minus, the other one has to be positive. And let's double check this. 2 cosine c times cosine c is going to get us 2 cosine squared c. Negative 1 times 1 is going to get us negative 1. So then our inner and outer terms, 2 cosine c minus cosine c will get us then cosine c. So that's awesome, which then implies that 2 cosine of c minus 1 is equal to 0, or cosine of c plus 1 is equal to 0, which means cosine of c is equal to negative 1, or cosine of c is equal to a half. Now, we are given the interval from 0 to pi, so within the interval from 0 to pi, which c values cause this derivative to be 0? Well, the first angle measurement that we get, c being negative 1, well, cosine at c to be negative 1 is actually going to be pi, because if we take cosine at pi, then we get negative 1. Cosine of 1/2, well, cosine of 1/2 only occurs one time on the given interval from 0 to pi. That occurs at 60 degrees, which means c is pi thirds. Great. So we found 2 values, but wait, there's an issue. The values that must exist that we just found must lie in this open interval, which means endpoints are not acceptable. And there's the issue. I'm going to say interval endpoint. Can't use it, which means there's only one possible solution, which means C must be pi thirds. And that's exactly it. That is the value that we are looking for. At C is equal to pi thirds, that is where one of these critical numbers will appear, and that is pi thirds. So there we are. We've answered the whole question. We found that value, did some awesome work on calculus and some awesome trigonometry work. So I hope you all enjoyed this lesson, and if you have any questions, again, please feel free to contact me. Have a great rest of your day, everybody.